Hello and welcome. We are making our way through our practice questions here. So let's start with an example from asymptotic notations where we're going to satisfy multiple constraints. So let's show that 3n to the 5 minus 10n is not an element of big O n cubed. As we often do, let's go ahead and start this off with our definition of big O. Whoops. So our definition of big O, there exists an m greater than 0 for, there exists an n naught greater than 0 for all n greater than n naught. F of n is going to be less than or equal to m times g of n. Given this definition, we want to make sure that we know that we're actually trying to solve for not big O. So if this is big O, we're going to solve for not big O. So when we not this, we end up with negating. We're going to flip those signs for all, there exists. Okay, and then we have f of n is strictly greater than m times g of n. Now, please just notice here that there exists, why do these things happen? This pen is not doing anything. Okay, well, please just notice here that right here we have there exists an n greater than n naught, and we have to make sure that this is going to hold true. Now, the negation holds true for all n naught and all m. So we no longer get to choose those values. We no longer get to bind those values to prove our statement is true, but instead we're going to rely on the fact that they exist and that they're arbitrary and use that to our advantage. Okay, so let's just rewrite the problem statement here, like this part here, with the actual functions in mind. So we're saying 3n to the 5 minus 10n needs to be strictly greater than m times n cubed. Now we're going to look at this and immediately we're going to notice that difference in terms right here. And when we see that difference in terms, we know we're going to need to get that factored form out. So let's go ahead and factor out that n to the 5. And so, a reminder that this literally is just factoring it out. It is exactly equivalent. These two are equal to each other. We are just taking out the n to the 5 and moving it outside those brackets there. And now what we can see we have is this glorious term right here. Now, normally in our previous videos, we've been working with fractions. We've been trying to, get this less than a half. Now, there's no reason to get this less than a half right now because this value right here is greater than 1, which means we can actually just make sure that this is less than 1, and that will be good enough. We have to work with halves sometimes, but when we don't, we should avoid it. Now, if we want to make sure that this term right here is less than 1, 10 over n to the 4 is going to be less than 1. Well, as long as the bottom is greater than 10, we know that it will be less than 1. And because I'm feeling nice and lazy, I'm just going to say n greater than 10. And I can say that because on the bottom here, we've got that n to the 4, right? So we know for sure that that's going to be less than 1. It's going to be a lot less than 1, but there's nothing that says that I can't do that. It's totally fine. We're trying to prove that there exists an n in this space. So let's just make that our n for right now. So I'm just going to put a box around this because this is an important bound that I don't want to lose as I'm working my way through this problem space. Okay, so now that I know that that's going to be true, basically what I'm saying is n to the 5, 3 minus 10 over n to the 4 is definitely going to be greater than n to the 5. Whoops, sorry, it switched for some reason there. 3 minus 1. Because if this is definitely less than 1, this whole thing is definitely bigger than 2. So then this is just going to give us 2. So what that ends up being is 3n to the 5 minus 10n is greater than 2n to the 5, which is hopefully greater than m times n cubed. So that's sort of what we've done so far. We've managed to find an n where we can prove that this and this, like that whole statement is true. That's what we have found so far. So the next thing that we want to do is we want to take these two here, and we want to find a way to prove that those two are that inequality holds to be true. So let's just rewrite that inequality for a second. 2n to the 5 is greater than m times n cubed. Now, in order to ensure that this is going to be true for all m and all n naught, we do need to make sure that our n value is bound by n naught and by m. So things that we can see that are true, if we can push ourselves out of that very messy fractional space, so a reminder that this is when n is a fraction value and we don't like that. If we can say that n is definitely going to be greater than n naught, we can push ourselves up and out of that fraction. N naught is 0, so n naught plus 1. There we go. We can push ourselves out of that fractional space and we can make sure that our n is definitely at least as big as that 1 there, right? We can guarantee that. And when we do that, we are able to say things like n to the 6 is greater than any number of multiples of n to the 5, which would be greater than no multiples of n to the 5, which would be greater than any number of multiples n to the 4, greater than n to the 4, greater than any number of multiples on n to the 3, greater than n to the 2. And so having that term of n being definitely greater than n naught plus 1 right here allows us to see that this term right here, which is this one, is definitely going to be bigger than this term right here. That's a weird line, like this. So that's awesome. That allows us to have this other lower bound of n that pushes us to see why this might be true. So let's do that. Let's assume that that's the case. But we're going to add one more step in, because while that's true, we still need to define m, because we still need to make sure that we are setting our stuff in terms of m. But we can see that m times n to the 5 is greater than n to the 5. So at least then we can say, I'm just going to grab our original statement right here with all of our extra pieces. We can then add in right here, 2 times n to the 5 is going to be greater than n to the 5, which I'm now going to compare to m times n to the 3. Now, again, unless I do something about this m, because it's supposed to be for all m, it's possible that a very, very tiny m could cause this to be a problem, right? So even though when n is greater than 1, as we just saw up here, if we have a very tiny m, we could find a way for this to no longer be true, which could potentially be a problem. Is that true? No, a very tiny n. A very tiny n, but so we are binding it by that, but we want to also prove it's true for m for that same reason. We want to ensure that we're accounting for all potential values of m in our solution. So what we can actually do then is we can just solve for n in terms of m, just to ensure that we have that final like lower m bound. So we take this and we can divide both sides by n over 3, and we'll end up with n squared greater than m. Now, all this tells me is that as long as I pick an n value such that n squared is greater than m, we should be good. So if I pick an n greater than m, it will also be true that n squared is greater than m. Again, we're looking for lazy ways to do this. So what we've now come up with is that we can let n equal the maximum between our highlighted values. We have an n naught plus 1, we have a 10, and we have an m. So we can say n naught plus 1, we can say m, we can say 10, and then we can put that plus 1 over here. So then we can observe that n is going to be greater than the maximum of those 3 terms without the plus 1 at the back. Now, I'm not going to show the whole proof because I've done a few of them like that. But at this point, this is where your official proof would have started. And at this point, we'd be able to do things like say, observe that n is greater than 10. And because n is greater than 10, we know this to be true. And then we can say, observe that n is greater than 1. And since n is greater than 1, we know this to be true, right? We know that this was true. Then we can restate it all the way out like this. And then we can say, observe the fact that n is greater than m. And then we can do this math over here to prove that that is also going to hold true. And as long as we can show that all of those hold true, we have then proven that our original statement of 3n to the 5 minus 10n is indeed greater than m times n to the 3 for all m and for all n not, where there exists some value of n where this will hold true, where n is going to be the maximum of those values right there. Okay, awesome. So that is the first sort of more complicated version of these. Head on over to the next video, asymptote 7, to see another example involving similar techniques. Thanks, everyone, and have a great day.